So we're going to calculate the volume of a right cylindrical cone with the same general formula we use for all volumes of revolution. It's the definite integral from the start of the shape to the end of the shape of the cross-sectional area of that shape times our variable of integration. So let's now apply this to a cone. Imagine we have a cone, and the radius at the bottom is r, the height is h. What would the volume of this cone be? Well, in order to set that up, we need to ask ourselves, which direction is it going to be easiest to do the integral? How should we set it up? Which cross-sectional areas do we use? Now we can see that if we slice it perpendicular to the height and parallel to the base, we are just going to get a bunch of circles that are of descending radius. And since we're doing this infinite integration, it would be necessary then to make this axis the axis over which we're calculating our volume. So if we cut it away as a triangle, what we've really got are a series of triangles like this. So this is our cone once we've turned it and got it along the x-axis. The point in the middle of the base is 0, 0. Down here it goes 0 minus r. Up here we have 0r. This point here is at h, 0. So what we're going to want is the volume of these, or the volume of the shape with the areas of these circles. So the area of this circle is going to be pi times that radius squared, where the radius here, again, is y. So we need to find an expression for y. Well, what we know is that it's a straight line. So it applies, the y equals mx plus b form applies. We also know that we can always find our slope given 2 points on the line, and that can lead us directly to our form. If we focus on the line at the top here, we can't do both at once because then it's not a function, it fails the vertical line test. But if we focus on the top, we see that our b is going to be r. And our slope is going to be, y2 minus y1 over x2 minus x1. It's going to be whatever it takes to hit this h0 point, starting from 0r. So we can let one point be 0r, our other point is h0, and our slope becomes a negative r over h. So this is an expression that represents the radius of our cylindrical cone cross sections. It's negative r over hx plus r. So that means our volume is going to be the integral from 0 to h of pi times the negative r over hx plus r squared dx. So this is the expression we're going to have to work with. We could start by saying pi is a constant. We could pull that out front. The r we have inside is also a constant, right? That is the radius of the base and the base alone. So we have an r overall in this factor. Because that's squared, we'd pull out an r squared to pull it out. So that gives us the integral from 0 to h. And if we reverse the order of terms inside because it's squared, that gives us 1 minus x over h squared dx. So now we have an integral that looks a little less intimidating. So v is pi r squared times the integral from 0 to h. Now we could do that with the power rule and chain rule and try to back it up that way. It is going to be easier just to expand out the inside completely and get this expression. So now we are just taking a direct integral of a polynomial. So v is pi r squared. And now, taking the integral, the x equals 0 to h comes out here. The integral of 1 is x. The integral of 2x is x squared. So we have a minus x squared over h. And then finally, the integral of that x squared over h squared, well, the integral of x squared is x cubed. We have to have a 3 down here to cancel it. We're still going to have a squared, and we'll be adding that. So this will give us our ultimate expression for the volume of the cone, pi r squared. Now, we evaluate these between 0 and h. So first we substitute h into all of these. We get h minus h squared over h plus h cubed over 3h squared. And then we subtract the values once x is 0. We see here that h, or the first term simplifies to h squared over h simplifies to h. These cancel. These are irrelevant. 2 of these h's cancel with 2 of those h's. And the whole thing suddenly and nicely simplifies to pi r squared h over 3, or 1/3 pi r squared h, as we are used to seeing as the equation for the volume of a cone. So once you understand volumes of revolution, it may take a little more time than knowing the volume equations from rote memory, but you'll never feel them necessary to memorize again. It's always going to be that balance. It's nice to have that safety net of knowing you don't need to memorize the formulas. You can derive them from scratch if necessary. So this is the introductory day for these topics, the 2 specific worked examples. In upcoming days, we will deal with the volumes of more complex shapes, where we're not going to be able to just simply look up the volume equation.